This is the college distance one. The file contains information or survey data on distance to college from high school, nearest college from high school, and then various other factors. And we would like to test whether the distance has an effect on number of years a person spends in education or number of years of schooling. Many of you guys are ready. That's good. Now, yeah, let's look at the first question. It says, run the regression of years of completed education, ED, on distance to the nearest college for females only. So this is for females only. In the data set, we have 3,796 observations. So these are the number of people. And a number of them are female, a number of them male. So if you double click on female variable, double click on female variable, this is a spreadsheet for the female variable, and as you can see there are 3,796 people. Now the first person is male because the variable female takes 0. Second person is a female because it's 1. So this dummy variable female takes 1 if a person is female, otherwise 0. And these two people are males, female, male, so on and so forth. Now, because this is about female only, we have to filter out males from the sample and then focus on female data. Let's run the regression quick. Estimate equation, and type ED as your dependent variable. Make sure ED is first, otherwise you are actually looking at the effect of distance on education. So type next dist and type next C, and we need the coefficient there for intercept. We need to include intercept because average education, when there's distance is 0, is also possible, yeah, in this data set. Now go to options. As usual, we want to have the standard errors to be robust to heteroscedasticity. So change ordinary to Huber-White. So this is from the options. From the options in the specification, equation estimation menu option, change to Huber-White. And now, if you click here, OK now, don't do that. It will run the regression for whole sample. We would like to filter out males. For that, we type if in the sample slot here, if female equals 1. Now this is telling EVUs to only take observations where female is equal to 1. Yeah, if you remember, we had 0, 1, 0, 1 in the female variable, the observations. So it just ignores zeros and takes ones only. Yeah, this type this in there. If female equal to 1. Is everyone happy with this? Everyone is with us? Yeah. Click OK now. Now, does anyone want to comment on the results, especially on the coefficient estimate, and tell us if the estimate is statistically significant by looking at p-stats and probability values, and also look at r-squared. Tell us something about it as well, please. And notice that sample is now 2070 only, out of total 3,796. So it's only considering the female participants in the survey. So does anyone want to comment, please? Any comments? Welcome. Is the coefficient estimate for distance statistically significant? Yes? No? No? Yes? Anyone? Okay, let's divide coefficient estimate by standard error, by its standard error. This gives us the t-statistic, 3.47. Is this greater than 1.96 in absolute value? So we reject the null hypothesis of equal to 0, so yes, it is significant. And look at the p-value for this t-statistic. Less than 5%. It's 0.005%. Yeah? So we reject the null hypothesis again. Yeah? Good. Now, what about r squared? Does it say anything about anything? Exactly. So it's only a fraction of the, yeah? This variable that we included, distance, is only explaining fraction of the variation in education. So we may need to add more factors because, well, yeah, there could be omitted variable bias on this coefficient estimate.
So, can you please explain again for the impact of a very small r squared?
Oh, the r squared doesn't imply effect. It implies it's a measure of the goodness of fit. It's a measure of goodness of fit.
So,
R squared is between 0 and 1, usually. A smaller value implies the model is not good. The whole equation here is not good for our purpose. We would like to have higher R squared. Higher the R squared, the better the model. And in this case, only 0.05% of the variation in education is explained by the distance. By distance variable, yeah? So we would like to maybe add more variables to see other factors may play an important role there, yeah? Okay, now this is not the story we're looking at. The story we're looking at is, what is the effect? Effect is 0.06, negative. So can anyone interpret this in context? We have a value 0.06. What does it mean? It's just a number, isn't it?
Is it in terms of kilometers or what?
It's miles.
So average distance increased by
A mile?
6 miles.
Oh, no. If average distance increases by a mile, number of years in complete education will decline by 0.06. Yeah, that's what you want, yeah? Okay, good. That's the average effect among the females. And remember, for the whole sample last week, it was 0.07. So female sample is smaller effect, has a smaller effect, right? Now, we've done that. Construct a 95% confidence interval. How would you do that?
Take a standard level.
Yeah, we do it in eViews now, yeah. How would you do that in eViews? Do you remember? I think you were in suits and boots at Okay, eViews. Go to view. Coefficient diagnostics. Confidence intervals. Click. And you have 99%, 90%, and 95% there. Delete the 2 on the sides. And click OK. If you click just OK, you just have 3 confidence intervals. We won't need the long one. I mean long window, so just leave 0.95. Okay. Coefficient estimate. This is called point estimate. This is the original that we had before, yeah? 0.06. And this is the interval estimate. We only needed this distance coefficient. Does anyone want to comment on this now?
So the coefficient for distance is between the confidence interval. So it's
It's 95%. That's between minus 0.1 and minus 0.02.
Sorry, say it again. 95%?
95% chance that the interval is between minus 0.1 and minus 0.027.
Mm-hmm. Okay. Anything else? Let's say you run the regression 100 times with different samples. And you get betas, distribution of betas. Every time you get a couple of beta. One is for coefficient, one of distance. So you take the distance coefficients and you put them in a, you look at their frequency. Relative frequency it gives us density, right? And if you want to create 95% confidence interval for that, you are basically saying that in 95% cases out of this 100 case, the true beta lies between minus 0.10 and minus 0.2027. Yeah. The true. Sometimes you will see people saying, "I have 95% confidence that the true beta is between 0.10 and 0.027." That's acceptable. And 0 is not in there, is it? The interval doesn't contain 0, so obviously this is another way of checking, doing a hypothesis test. If 0 is not in there, we are ruling out the effect to be 0. We're rejecting that, yeah? So that's why we reject the null hypothesis of beta equal to 0. So beta is not equal to 0 based on this fact here. Well, estimates, not a fact. We only have 95% confidence in this estimation. All right, next, we go to B now, if you do not have any question. B. B says, do the same thing for males only. So go back to estimate, click here, estimate here at the top. And if you go down to the sample slot, again, this one here, and delete 1 and type 0. Now we're telling eViews just show us the observations where a female is equal to 0. So just males. Yeah, we want the male sample only from the whole sample. Okay now. So if you type 0, then okay. Wow, this is great, isn't it? 0.08. So the effect among the boys, yeah, for the boys, education is higher. So boys are a bit lazy. Yeah, traveling is an easy task. It's not an easy task apparently. Anyway, that's an anecdotal effect evidence. So look at this now. Boys are fewer than girls in this sample. 1,726, a smaller sample, but that's big enough for us for statistical inference. And also R squared a bit larger as well, but that's still minor thing. But what's important is that t-stat is greater than 1.9. So if we have a 5% level significance, so rejected at the 5% level, yeah, we reject the null hypothesis at 5% level, and even at 1% level, that's fine. Okay. Now the question is it really different effect between males and females? So we have the female effect 0.064, male effect 0.084. So effect of distance between male and female is different, isn't it? But the question is it statistically significant? Is this difference statistically significant? So we need to do hypothesis testing again. Right. Keep this in mind. I'll switch to now drawing board and I'll ask these questions in a minute. Right, this is for the next exercise. So we'll go to this. Let me fade this out. Okay. Question number C that we're looking at now. Let's see. That's C basically we're doing now. So we did the B, so we jumped into C. Now we know what we know so far is this. We learned that beta hat F coefficient estimates for female is 0.064 negative. Also beta M is minus 0.084. And also standard error beta F. What is standard error for this? Does anyone want to tell me what the standard error was or is? If you just quickly go back and run the regression. In the meantime, I have the standard error for boys coefficient, male. It's 0.02, I think, yeah. What was this one, female one? Can you quickly run the regression and tell me, please? So the first equation that we calculated or estimated. Standard error for the coefficient estimate. Thank you, 0.018. Right, we need these two. Now, next. The null hypothesis is that we usually say in the null hypothesis, state them in population terms. Is that there is no difference between the betas of male and female, so they are equal. Alternatively, in a two-sided test, we say they are different. Don't put the hats. And this could be rewritten as beta F minus beta M equal to 0. If I just put the beta M to the left-hand side of the equation, right? Now, then, the testing of the hypothesis would be something like this. Because we're looking at the difference, so we need to find the difference between the beta coefficients and its standard error as well. We know from this information what these values are. What we don't know is the standard error for the difference. What is this? That's what we don't know. But we can calculate it. Because these estimates are obtained by male and female samples, they are independent. They do not correlate. Yeah. So basically, what we're saying is covariance between these two random variables is equal to 0. And in that case, variance of the difference will boil down to this thing. I shouldn't have put the covariance, but let's put just for the sake of understanding it properly. Right. Because this is 0, we will then have variance of beta 1 hat, sorry, beta f hat. Is it plus? Yes, variance of beta m hat. And this would be 0. If you use this standard errors, square of standard error is variance, yeah? Square of standard deviation is a variance, yeah? Standard error is actually estimate for standard deviation. So this would be now if you square root this gives us this thing. That's what we needed, and we have it now. So we need a standard error of the difference between the two. Then we just plug that in here. Something like that. So we have the t-stat now. Now it's decision time. If our t actual is in absolute value 0.74 and alpha equal to 5%, t critical then it will be 1.96, then t actual is certainly greater or less than t critical. So reject null. Well, H null. So we reject the null hypothesis of no difference. Oh, did I do it right?
Insufficient evidence to reject.
Why? Guys, did I do it right?
No.
Thank you. No. Failed to reject.
Why?
It's failed to reject, isn't it? Clearly. So let's say accept. Usually we don't accept it, yeah? We don't accept the statistical evidence. We just give it some probability of confidence.
Is it better to say like
No, if you reject the null hypothesis, means there is a difference. There's a statistical evidence of difference between the effect of education distance on male education and female education. But because we accept the null, now it implies there is no difference between the effects. So this statistical evidence suggests that the effect of distance on male and female is the same.
Can you say reject H1?
If you reject H null,
No, the alternative.
you can't reject H null. You can't fail to reject or reject H null only. Alternative is what you want actually.
Oh.
It's your research question.
Oh.
Usually, yeah. It's the null hypothesis that you need to reject or accept. If you reject, obviously, you just go with the alternative all the time. In this case, we won't be going with the alternative because this evidence suggests the effect is zero. The difference is zero basically in the effects, right? Sorry, it's just for some reason my brain malfunctioned, and that's what happens when it does. So make sure when you watch the videos you realize the errors. Sometimes I put the bubbles saying, okay, there's an error or something like that on these videos. Okay. No question, we go to the next one. This is from the first class that I had this morning, so just kept it. The stars, that's what we need to do, but then we'll leave them now. Right, let's look at the question number 2. It says add a star for 5% and 2 stars for 1% significant levels. If the coefficient estimate is significant at 5% level, then you put 1 star next to it. Otherwise, 2 stars. Or nothing, if the evidence is that we do not reject the null hypothesis. Okay, how would you know, or how would you calculate t-stat? Because we need to calculate the t-statistic and compare it with the critical value to make the final decision about the rejection or acceptance. Yes.
You take the value and divide by standard error.
Which value?
546, for example.
Okay, so let's look at the first column and the. So by the way, these are regressions. So just to give you, thank you. I'll come back to you. Average hourly earning is our dependent variable. So basically, we have AHE equal to predicted AHE. I'm doing the first one now. Intercept is 12.69, right? 12.69 plus. So this is continuation. 5.46 times college minus 2.64 times female. Right? This is the equation basically. Now the question is, are these coefficients statistically significant? If they are, at what levels? So we need to indicate them by putting the stars. So the second regression model will include the third variable age. So if I wanted to do the second, I just add the age coefficient and change this and change the values. And the third, so there are 3 models. We do it for the first one. So let's do the test, t-test, hypothesis test. Okay, I just did this. T is then 5.46, as your colleague said, over 0.21. And this is something like, what do you think, guys? What's the value for this? 26. Wow, 26. So T actual is 26, and T critical for 1% is 2.58. This is greater than 2.58, right? So you put the 2 stars next to it. And these 2 stars imply basically this all coefficient estimates are significant at 1% level. We put them in the first class, so you just, if you have printed, do this stars on the, put them on the paper. Otherwise, do it at home when you get home and print. And the coefficient for northwest has a 1 star, has a star basically. This is because this is only significant at 5% level. So if you divide 0.69 by its standard error in brackets, you get, what do you get, guys? 2.3, which is greater than 1.96 for 5% level of confidence, sorry, significance, but it's less than 2.58 for first 1% level. So we only include 1 star because of 5% level significance in this too. And this here is not significant at all, coefficient, or for the south, 6th variable is not significant, so no stars on them. But the intercepts are all significant at 1% level, so there are stars. Good, done this.
Excuse me.
Yeah.
Why do we have a critical value of 2.58?
This is from the distribution table, T table, or in this case, standard normal table, because we have a large value observation.
Is it like under 1%?
Yeah. It is for 1% significance level. If you look at the 1%, it has a value to the left, 2.58. Yeah, no worries. And also, there's a video I uploaded how to find this T critical values. If you look at, if you watch the video. Right, next question. We're running out of time. Quickly, guys. Number 3. Can I go and start next one? Number 3 says, calculate adjusted R squared for each of these. If you notice, what you don't have is in the table is the adjusted R squares. We have the R squares. Would it be useful at all having just R squared? What do you think? It won't be, yeah? Because for multiple regressions, multivariate regressions, we need to use adjusted R squared to sort of measure the goodness of fit. One. Okay, why is it doing this? Did I? Okay, sorry. Yeah, it should be here. Should have started here. And this is R squared, yeah? Formula. Now, what do we need to calculate for adjusted R squares? The formula for it is this one. So, the only difference between R squared and adjusted R squared is this here. Sorry, say again? Yeah, where do we get SSR and TSS? We don't have them, do we? But we have two formulas. So we can solve this one for SSR and TSS, plug that into here. So find SSR and TSS using this formula and plug it into this. So in that case, SSR over TSS, sorry for the handwriting here, bad, is this, yeah? And adjusted R squared is then 1 minus n minus 1 over n minus k minus 1 times 1 minus R squared. And we have this already. Yeah, we have also R squared. And we have n, we have k. All we need is just calculate the adjusted R squared for each of these. So sub 1 is basically first column. We have n equal to 4,000 given to us. 4,000. And k is the number of regressors. It excludes the intercept. So there are 2 in the first column, female and college. 2 minus 1 times 1 minus R squared. What is R squared for the first column? 0.175. 6, sorry. That's the result. For the second equation, 1 minus 4,000 minus 1, 4,000 minus 3, minus 1. Now we had age additional k is 3 now because of age. How many variables do we have in the last column? 6, right? You have x, 6 x's basically. That's it. Now the question is, which of these models, 3 columns we have, yeah, is the best, or the one that we want to pick? I assume you have read the question, yeah, what the variables are. Yeah. So which one of this?
No,
Third one. Why?
because it shows you the highest. It's just the best people. Not all of them.
So the coefficient of determination, r adjusted r squared, right? This time is higher, right? So 19.3% of variation in the hourly earnings on average hourly earnings is explained by the variation in the whole model. By this, the whole model consists of these variables, 6 variables. Yeah,
What does this explain again?
it explains 19.3% of the variation in earnings. By the way, adjust r squared doesn't explain it. It just shows you that 19.3% of the variation in earnings is explained by variation in this 6 variables jointly. Yeah, by the model. Yeah, the highest is that one. So we go ahead with the last one. But then this is not a complete model, so you can always add something else to it. Religion is missing. In some cases, earnings depend on religion. For example, if female variable, for some religions, female people, women don't even work. Yeah, look at this is U.S. data. So in the U.S., Mormons don't work. Yeah, I don't know if they at all go to college, but they usually don't work. So their college degree will be 0. Their female will be, although 1, but it will be a very negative number, I think. And age, well, yeah. Anyway, so this is average effect. It includes everyone, but then I would add more of different factors. Yeah, you can think of different factors that could affect hourly earnings. Yeah. Right. Any questions? Number 4. If you do not have any questions, let's go back to this. And number 4 is uses the information from the table. So we need the table again. Can you read the question and try to think about the first question? A. A says, using the regression results in column 1. So we're looking at the column 1, first model. Do workers with college degrees earn more on average than workers with only high school degree? What do you think?
They should.
They should or they do?
What's the coefficient for high school? Is it like your intercept?
The variable college takes 1 if person has a college degree, otherwise 0. So it must be some interesting result here, right? What do you think, guys? I'm sorry? Let's let's hope. So you're doing college, aren't you? Let's hope that it works out. That's a good point. So what do you think? This is from America. So let's say if it worked for them. From
How did you find that?
okay, you see the. Let's work out this thing, guys. Let's rewrite the equation. If that's difficult, then let's do this. Average. So this is average hourly earnings, right? Average hourly earnings hat is equal to intercept for the first column is 12.69. Well, mine is becoming a point is becoming a comma for some reason. Plus this thing here, 5.46 minus female. So this is actually college, right? College. Let me write it. Minus 2.64 times female. Now, coefficient on college is what we're looking at now. The college takes 1, variable takes 1, value 1, if person has a college degree. Otherwise 0. Let's work out what the average earning for a person without a college degree. Well, let's see. Let's see. So this is 12.69. If a person has no degree, then plus 5.64, 46, sorry, times 0. Ignore the female part. So this is 0, isn't it? This is 0 because this is times 0. If a person has a college degree, plus 5.46, it will be times 1. So the on average person with a college degree earns $5.46 per hour more than a person with just high school degree. This is on average. Yeah, this is the difference. $5.46 per hour. We answered that question. How much we answered that question? Is the earnings difference estimated from this regression statistically significant at the 5% level? What do you think?
You take your 5.6 and back down there.
We have the 2 stars already, right?
Yes,
Yeah, it's a strong evidence. It's even statistically significant at the 1% as well level. So yes. Now B. Do men earn more than women on average? Now we're looking at the coefficient estimate of female. If a person is female, this value takes 1, this variable takes 1, otherwise 0. What do you think? Now look at this now and focus on this only. The negative sign should be there, but yeah. Minus sign should have been included in this circle, which I missed. So we're looking at this now only. What do you think? Do men earn more than women on average? Yeah. If a person is a female, they earn $2.64 per hour less than males. Yeah. I don't know that though, but yeah, sample shows there is some sort of gap. You know, there's a nice word for this. It's called gender gap, not a discrimination. Yeah, it's a bad word, but it probably means the same thing. To be politically correct, gender gap. I think that's what they are fighting for now. They want to reduce that gender gap, especially in this country. I don't know in the US, but in the US, the statistical evidence suggests there is something. But obviously, this is not the final model. We can add a lot of things, and the difference may be because of not gender, but something else, which we are not including. And notice that there's big room for improvement. Our R squared, adjusted R squared, is still below 18% in the first case. So we want to be 100% sure. So we want to increase R squared to up to 99.999. Then we can make a decision, yeah, whether there's a gender gap or not. If this female variable coefficient estimate is less, not significant at 5% or 1% level, we could have even ignore, there's no gap. Even if there's a large value, if it's not statistically significant, no, it's just sampling variation. It's because of sampling variation. Take another 4,000 people and run the regression, you will see a different value, if not bigger. If you go to Bankers, Canary Wharf, and maybe you get something different. Okay, any questions? Yeah, men earn in this sample more. Okay, it's statistically significant. Question number 5. Can you please read it? Okay, I am. Question number 5. So we're looking at the second column now. Look at the second column. It's a bit longer model now. We added age extra. This is, we calculated this is 0.189. Now, is age an important determinant of earnings? Yes, no, yes, no. Guys, it's only one person saying yes, but is it no or? It appears age is an important variable because it's statistically significant at 1% level, right? And also, do you want to comment on the coefficient estimate? How would you write in your essay, let's say in exam? What's the effect? What's the effect? Economic effect. What's the economic effect? Quick, anyone? An increase in the age by a year will increase the earnings by 29 cents per hour, regardless of the gender, right? Or anything, because we're holding them constant for now. We're only looking at the partial effect of age. So this implies on average, an increase in age by a year increases person's earnings by 29 cents an hour, holding other factors constant. This would be a complete sentence, I think. If anyone can rewrite it in a better way, that's even better. Now, let's go to the next question. B. Okay, this is a situational exercise. I mean, the case study. Sally is a 29-year-old female college graduate. So pay attention, it's a female college graduate. So there are two variables, college and female. So we will need to keep this in mind. And Betsy is also a 34-year-old college graduate, and she's also a female as well. Yeah, this person is also female. Now predict Sally's and Betsy's earnings. Predict Sally's and Betsy's earnings. What are their earnings, guys? What are their earnings? So let's work out earnings for first Sally. S. AHES. 4.40. This is from the first column. Second column. It's the intercept, right? Plus 5.48 is a coefficient estimate for female times. Is Sally female? Yes, so 1 minus 2. It's college, isn't it? So Sally has a college degree, so 1 minus 62, 2.62. And she's basically female, plus the coefficient on age is 29 times. How old is she? 29. And predicted earnings is 67, yeah? Per hour, this is how much she will earn. Average earning. This is now Betsy, AHB. She has a college degree, also a female, otherwise this would be 0. This is dot is product, indication of product. And she is now, Betsy is 34. And her average earnings is expected to be 17.12. These are dollars per hour. Note that the only difference here comes from what? The only difference, because these are the same, given their gender and degree, they should earn the same amount. But because the age is different, yeah, Betsy is 5 years older than Sally, she is going to earn a little more. How much does she earn more? How much more does she earn? £2.50. Oh no, it's the opposite, isn't it? I'm doing the opposite way. So what's this? Now this is 5, and this would be 4, isn't it? Let me clean this. What's the difference between them, guys? 145, right? 145. This should be negative, but it's just, yeah, Betsy earns more, so we just did the opposite, yeah. 145. Age gap, yeah. This is the effect of gap, age gap. No, it's actually, we said extra age gives you extra cents, yeah, 29 cents per hour. So 5 times 29 cents per hour gives you 145 extra. So she earns $1.45 more because of older age. Okay, guys, we'll continue from this point on next week. And if you please return me your register, that would be great. Thank you.